Hi, I'm Robert from Queensland University of Technology, Australia. In this video, I will be presenting our paper, Learning Arbitrary-Goal Fabric Folding with 1 hour of real robot experience. Fabric manipulation research has a wide variety of potential real-world applications, such as laundry automation and clothing manufacturing. Fabric manipulation is particularly challenging due to complex dynamics, which make state estimation and simulation very difficult. Learning-based approaches are particularly interesting in this area, as hand-designing controllers can be extremely expensive and time-consuming. Many prior approaches rely heavily on simulation, which is limited by the sim-to-real gap, as well as human demonstrations, which are expensive to collect and difficult to scale. In this research, we work towards removing the reliance on both. We would like to train fabric folding policies that can learn from a limited amount of real-world experience, and generalize to unseen goals. We break the process into 3 stages. First, we collect an hour of random experience data with the robot. This involves the robot acting randomly without any goals. We then use this collected dataset to train a goal-conditioned deep Q network. Then, we deploy this train policy on the real robot and evaluate it by giving it a set of unseen goal configurations. We parameterize our deep Q network as a fully convolutional neural network and, inspired by Zhang et al., we rotate the image through k different angles in order to produce a set of Q heat maps for each discrete action orientation. However, in the fabric manipulation setting, we also require a variable folding distance. We extend the prior approach by additionally scaling the rotated input images through s different scales. This results in k times s output Q heat maps. We take the argmax over these heat maps to retrieve the pixel location, angle, and scale for each action. Scaling the images to achieve variable action distance is effective due to the equivariance properties of fully convolutional neural networks. As shown in this diagram, when an image of a folded towel is scaled by half, it closely resembles the smaller fold seen below. Similarly, the corresponding action is twice the size. With this method, the network only has to learn one set of features for a fixed length fold, and we can manipulate the input image to achieve a variety of folding distances. To train this Q network on offline data, we use hindsight experience replay with a sparse reward. We sample experience tuples from the dataset, consisting of observation, action, and next observation. We then sample a goal by either sampling a random observation from the dataset, or we use the achieved next observation as the goal, with equal probability. If the goal is the next observation, the transition is labeled with a reward of 1, otherwise 0. Our discretization approach and use of fully convolutional networks allows us to avoid some of the typical pitfalls of batch RL, which is known to be particularly bad in continuous action spaces. At test time, we deploy the policy on the real robot with a set of 6 unseen goal images. Here we show some successful trajectories for a subset of them. We compare against prior work by Ganapathy et al., which solves similar tasks by using both simulation and human demonstrations. We show that our approach performs competitively using only an hour of real-world robot training data. Our method consistently solves the first 4 goals, where the required actions are clear when observing the goal. However, the final 2 goals are significantly more challenging, as the folds required are not directly visible in the goal image. For these experiments, the robot's action space consists of 8 orientations and 3 scales. However, we demonstrate that our method can generalize to a more precise and higher resolution action space at test time without further training. In conclusion, we present an approach for learning goal-conditioned fabric folding policies using only an hour's worth of real robot data. We demonstrate a method for effectively discretizing the folding action space in combination with a fully convolutional Q network pipeline, which allows the policy to learn from a sparse reward function without requiring simulation or human demonstration data. Our approach is able to solve a set of challenging unseen goals at test time. In future work, we would like to address several limitations, such as generalizations to fabric of different colors and materials, as well as improve the performance on more challenging tasks. Thank you for listening, and please see the full paper for more details.